Hello everyone, I am Mukhtar. In this tutorial, I am going to present image classification by using machine learning neural networks. There are many machine learning algorithms which can be applied to image recognitions or classifications. In most of them, an image will be input to the network, then the input image will be classified into one of the predefined output categories. For example, an image of cat will be classified into cat category. An image of dog will be classified into dogs category. In this kind of networks, a whole image will be passed into the network as an input data and then classified into a specific category. As we know, there are many image types including medical images, satellite images, etc. In this tutorial, I want to classify a single image into several categories by using neural networks. For example, if we search medical images from Google, we may get many images. In fact, there are many medical image types as well. This is a medical image from Wikipedia. If we see this image carefully, there are different tones and textures. For example, these very bright areas represent very high grayscale values and represent a specific texture. These gray areas represent specific textures and have medium grayscale values. These dark areas also represent different textures and should have lower grayscale values. So, there is different information in an image, and we can extract them by using image classification methods. In this tutorial, I want to build a neural network which is able to do the following. First, I may use it to classify an input image into different output categories. I may use it for change detection between time series images, including medical images as well as for satellite images. I may use it for extraction of specific target from an image. In addition, I may modify it and create a modified neural network which fits a specific usage. For example, please see this image. There are some roses in this image. This is the big rose. See these small roses as well. I may extract them from this image. See these extracted objects in red. They are the roses extracted from the original RGB color image. Of course, if we extract targets from the time series images and compare them, we know the changes of the target objects during the time range. This is very useful for medical images especially. That's the aim of this tutorial. In above, I mentioned the satellite images. Now, let's check that. It was taken by the French satellite Spot, sometimes called the Spot excess image. Namely, Spot has three channels or bands in visible and infrared regions of the reflectance spectrum. Then, the bands may be composite and assigned to RGB colors. Thus, different types of composite images can be generated. This is a false color composite image. I don't give more details about the color composite of the satellite images here. However, this false color composite image allows vegetation to be detected readily in the image, and vegetation appears in different shades of red depending on the types and the conditions of the vegetation, since it has a high reflectance in the near infrared band. I will use satellite image for a demonstration purpose here. I have bought this image previously and I have right to use it. However, the image credit or copyright belongs to QNES. In fact, the neural network, namely the classification algorithm, which I am going to build, can be applied to other image types including medical images. We can classify to some change detection analysis or extract the disease areas by using the same classification method I use it in this tutorial. If we use medical images to train the same neural network or add some necessary modifications to the same network. Please see this picture. Now, let's start. First, I would like to divide the whole process into several steps for easy understanding. Step 1. Read the image and get samples for each category. Step 2. Define some hyperparameters, for example, number of hidden layers, nodes or neurons in each layer. Step 3. Define variables and placeholders for the training process of the neural network. Step 4. Build on the neural network. Define hidden layers, output layer, weights and biases along with loss and accuracy related variables and placeholders. Step 5. Now create a session and initialize all necessary parameters. Step 6. Now we are ready to run the process and train the neural network. Step 7. After the training process has been completed, I will save the training network. This is the end of the building and the training processes of the neural network. Step 8. This is an optional process. I may plot the loss and the accuracy histories of the training for visualization purpose. Step 9. This is very important process. Now I have the trained neural network. I am going to use it. In order to use it, first I need to restore the saved trained network. Step 10. Validate the neural network by using some practical data. Step 11. The final step. Deploy the network and use it to predictions. Let's start build the neural network based on the steps mentioned above. Actually, I have written the code in order to save the time. This is the code and I will explain it line by line in the following sections. First, we need to import some Python libraries. Import NumPy, import pandas, import image from PIL, import TensorFlow, import matplotlib. Finally, import shuffle label encoder from sklearn library. Okay, then where and how we get the training samples from an image. Step 1. Namely, read the image and get samples for each category in the image. Please note that I am going to explain the step 1, the data preparation section, very detailed, since this is a very important process for a neural network in terms of training and accuracy. This is the input image. I have used this image for research previously and I have grown the truth data about the land cover types of this target area. This is one of the reasons I am using this image in this tutorial. Now let's see the target image. This area represents water. I get sample from here for water. And this area represents forest, so I get sample from here for forest. Then this area represents bare land. I get sample from here for bare land. This area represents wetland. I get sample from here for wetland. These red areas represent crops, so I get sample from here for crops. Let's see these very strong white areas. Actually, based on the ground truth data, these areas represent dried salted surfaces. I get sample from here for dried salted surface. These areas represent grasslands. I get sample from here for grassland. Therefore, I want to classify this image into 7 categories mentioned above. Then I will assign a color to each category. As a result, there will be 7 colors in the output land cover map. Please note that getting sample is simply meaning to cut a rectangular area from the corresponding areas for each land cover type as mentioned above. Now let's see the code and the sample for water. We may create a function for this step. Give a nice name. Open image, extract training set. First, open the image and convert it to an array. Please see here, I am opening the image, then converting to it an array by using the NumPy's array functionality. The output array name is IM. This is the array size. Actually, this array is a 3-dimensional array. This is the height, this is width, and this is number of bands. The height is 371 pixels, width is 781 pixels, and there are 3 bands, RGB. Now I have the array IM, so I can cut sample area for each category and generate input data examples for training. First, get sample for water. I am cutting a rectangular area. It starts from 112 through 136 in Y direction and starts from 306 through 321 in X direction. And we have 3 bands, RGB. As a result, we have a row of 24, 15 by 3. Now, let's see this line. Namely, I am concatenating the row along with axis 0. Here, axis 0 means the y-axis or vertical direction. As I mentioned previously, IM array is a 3-dimensional array. After we got the row, I am concatenating the pixels along the axis 0 direction here. Why I am concatenating them along the axis 0 direction? Now let's check that. This is the original Spot XS image. Copyright belongs to QNES. First, I open the image, then convert it to an array IM. For example, I am going to cut an area of 3 by 3 row. Let's suppose that the row is the cut area. If we print the row, we get these 3 by 3 matrices. Actually, each matrix represents a subset or window on each layer in the image. So, this represents a 3 by 3 window on the first layer. Please see this 0 index. This portion represents the second subset on the second layer. Please see this index 1. And this represents 3 by 3 window on the third layer. Please see this index 2. There are mainly 3 types of encoding of raster images. They are band interleaved by pixel, BIP, band interleaved by line, BIL, and band sequential, BSK encodings. However, this image is encoded by using band interleaved by line encoding. So these blue pixels belong to the blue band, these green pixels belong to the green band, and these red pixels belong to the red band respectively. If we see this single layer, these blue, green, and red pixels are interleaved by lines. Therefore, here I am going to concatenate the same pixels which spread over the 3 layers and create the combined pixel values for red band. Do the same concatenations for green and blue bands respectively. After the concatenations, these pixels 0 includes combined red pixel values, and this pixels 1, please see this index 1, includes the combined green pixel values, and the pixels 2, please see this 2 index, includes the combined blue pixel values. Finally, I am able to get a data set like this. In this data set, now this column represents all red band pixel values. This column represents green pixel values, and this column represents the blue pixel values. Finally, this column represents label or desired output values. We will see this later. Let's return to the code again. So, in this pixels variable, we have the combined pixel values for water sample. Now, from this, I am going to generate the final training data set for the water sample. For this, I will generate a dictionary like this by adding the desired output column to the end of the dictionary. Actually, this is a pandas data frame. Please see this line. I am going to create a dictionary. This dictionary has 4 elements. The first element is red pixel values. Please see this index 0. Second element is green pixel values. Please see this index 1. The third element is blue pixel values. See this index 2. And the fourth element is the desired output name. For example, water here. Okay. Please note that the last element of the data frame again. I have added the label water to this column. Now, I got the training data set for the first category water. I do the same thing for all remaining categories. See the data set for forest, bare land, and others as well. Until here, I got sample for each category. Now, I need to concatenate all categories and generate a single dataset. For this, I need to concatenate all data frames from df1 to df7 and get this data frame df. If I save the final data frame of df in CSV format here, then open it with Excel, I just get an Excel spreadsheet as this. Now, please see this Excel sheet. We have 4 columns: red, green, blue, and this is the desired output column. Sample data have been arranged in terms of bands including red, green, blue, and desired output labels. The final data preparation step is I need to encode the desired output to a one-hot format, since the last column is not in digital format, but strings that represents the desired output category names. Therefore, I need to convert them to digits by using the one-hot encoder. Let's see the code. Here I am dividing the sample data into 2 parts. First, set swap inputs, or RGB. I can get this from the data frame with the indices of 0, 1, 2. Please see here, df.columns. Please see these indices. Second, desired output. I can get it with the index of 3. Please see here, df.columns, 3. This corresponds to the desired output column in Excel sheets above. 3. One-hot encoding. Actually, one-hot encoding transforms the desired outputs into a new format or vector of ones or zeros. As a result, the desired output is the hot, 1, and while the rest are zeros. For example, the string of water, the desired output category name, will be converted into a vector like this. This vector has 7 elements. Please see the first element. The first element is 1. The rest are zeros. The string of forest, the second category name, will be converted a vector like this. Please see the second element. It is 1, and the rest are zeros. And the third category, bare land. The string of bare land will be converted into a vector like this. Please see the third element. It is 1. The rest are zeros. This is the aim of this encoder. In order to achieve this, first we need to initialize the label encoder object. Please see this slide. Then get the total number of labels. Please see this slide. And then get the unique number of the labels, desired outputs. In our case, it's 7 in the slide. Please see this. Then create one-hot encoder matrix. Please see this line, all zeros, using this numpy zeros function. Then set ones and generate unique vector for each unique output. Please see this line. This function returns a pair of dataset, RGB values, and the desired outputs, one-hot. Now, the open image extract training set function has been completed, and this function returns us 2 datasets. One more thing, I need to shuffle the data so that randomize the input data, and this will be speed up and increase the training accuracy. Now, let's see step 2. In this step, some hyperparameters are defined. For example, learning rate, here 0.03. Number of training epochs, here 300. N underscore RGB represents the number of parameters, RGB. Number of hidden layers, in our case, it's 4. And the number of nodes or neurons in each hidden layers. Please see these numbers. Desired output categories or nodes, it's 7 in our case. And the saved path and the file name to save the trained network after the network training completed. Define a container, accuracy underscore hist to store accuracy history and its changes. Step 3. Define variables and placeholders for the training process. See this equation. Each variable and the coefficient, namely matrix and the vector, have to be defined. The x is placeholder for batch input, while w is for weights, b is for biases, y underscore is for desired outputs. Here the none is equal to the number of input samples. These will be used during the training process. Here defining weight and bias dictionaries for each hidden layer. These are the size of the weight matrix for each layer. Weight dictionary includes H1, H2, H3, H4 and out. And the bias dictionary includes B1, B2, B3, B4 and out. Now I have defined the variables and the placeholders based on the model. Step 4. Create a neural network with sigmoid activation function. Here the variable of x represents the net input calculated by the summation operator of a node, and fx represents the output squashed value. There are many different activation functions in TensorFlow. I don't give detailed information here about the activation functions. You may see TensorFlow documentations. Now let's build a network as a Python function, multi-layer network. This function accepts three parameters. X is the input data, weights, and biases. Then, first the input data x and the weights will be multiplied, and the biases will be added. I denote this sum with a variable of sum underscore 1, since this is actually a matrix multiplication or summation operator. Please see this expression here. Then the sum underscore 1 will be passed to the activation function, and then it will be squashed within the range. Therefore, in each node or neuron, there are two operations, summation and activation function. The activation function limits the output of a node to a certain range. Here I am using sigmoid function or logistic function. This function produces output between 0 and 1 whatever the inputs are. These are for hidden layer 1. Okay, I do the same operations for the hidden layer 2, 3 and 4 respectively. Finally, using the hidden layer 4 with other parameters, the output layer and the values for its nodes will be calculated. Please see out underscore layer. Then the function returns the output layer. This is the neural network to be built. Namely, now I have an input layer, 4 hidden layers, and an output layer. Then the sigmoid activation function has been used in this network. Step 5. In this step, initialize all variables. Create a saver. This will be used to save the final trained network. Call the network and define the prediction by passing the input data set, weights and the biases. Define the loss. Actually, this is the difference between the prediction and the desired output value for each category. Here, y represents the prediction and y underscore represents the desired output. Define the loss function. The loss function is actually the process of the reducing the loss. Define the training process. Here, please note that I am using gradient descent optimizer. This function accepts learning rate and the loss function as input parameters. Actually, the gradient descent optimizer will minimize the loss function. In other words, it will find a global minimum value. There are many optimizers. See TensorFlow documentation in detail. Step 6. We will do some important operations in this step. First, create a session. Then run the session by passing the init object above, namely the initialization of the variables here. Now, it's time to create the training epoch loop. A training epoch stands for one forward and one backward pass of available training examples in a neural network. For example, I am training a network to classify an image, and I have a set of 1000 input data or training examples. An epoch will have occurred once all of the input data are passed through the network, including both in forward and backward directions. Let's see the loop. The number of loops equal to the training epochs defined above. It was 300. This is a session just created above. I am running it by passing two parameters, train network and the feed dictionary. The train network has been defined in step 5 above. I am using gradient descent optimizer in the train network object. Feed dictionary. This is the training set to be passed into the network. Please note that I am passing both the input data X and the desired output Y underscore, namely RGB and L respectively. Since this is a supervised training and each training example is a pair of input data and the corresponding desired output. From here, it's about the accuracy. Here I am comparing the prediction and desired output and getting the correct prediction. Then, based on this information, accuracy will be calculated. Finally, all accuracies during the training process are appended to get the accuracy history as this. This is the ending of the training epoch code block. In this part, I am printing the training process, epoch and the training accuracy in each 50 epochs or counts. Step 7. After the training process has been completed, the trained neural network will be saved to this save path. Step 8. In this step, accuracy history will be plotted for visualization purpose, since they are good indicators of the training procedures. Now, let's run the code and see. It's running and training the neural network. Finally, the trained neural network will be saved. Now we are waiting. Until then, I will show you some references. If you like to see more videos related to the machine learning and the neural networks, there are some very good references for you. Please see these references. Now, it is printing the epochs and accuracies at that point of the training. In the next lecture, I will restore the saved trained neural network and use it for predictions. Thank you for your listening. Please subscribe. Have a great day.